Hey everyone, this is Dr. Walker. In this video, we're going to go over example number 2 from video 574 on right-hand rule number 2, which lets us find the direction of the magnetic field produced by a current-carrying wire. In this example, we have 3 wires. They each carry the same current of 2 amps, and we can see from the picture that each current is going into the page, and they're placed along the corners of a square. The length of each side is 1 centimeter, which is 0.01 meters. We want to find the magnitude of the magnetic field produced at point P. So this is not just a finding a directions problem, we also have to find the magnitude. We learned that the magnetic field due to a long wire, we can assume that these are long wires with the current going into the page, is mu naught I over 2 pi r. So if we look at wires 1 and wire 3, they are the same distance from point P. So the magnitude of those fields is going to be the same, where we're going to use a distance of 0.01 meters for r. So let's go ahead and plug in our values. Mu is 4 pi times 10 to the negative 7. The current is 2 amps. And then the radius is 0.01 meters. Plug this in, we're going to get 4 times 10 to the negative 5 teslas. And this is for B1 and B3, so we can say B1 equals B3. For B2, the difference to find the magnitude is that the distance is different. We now have the hypotenuse of the right triangle, which is going to be 0.01 times square root of 2 for the hypotenuse, which is 0.01414. We can plug that into this expression here. We're going to have 4 pi times 10 to the negative 7 times 2 amps over 2 pi times 0.01414. And that's going to give us 3 times 10 to the negative 5 teslas. So you may be thinking, well, we only have to find a magnitude, let's just add up these numbers and be done. But the direction also matters. Let's look at the direction of each field. We're going to use right-hand rule number 2 and point our thumb in the direction of the current. So you should be pointing your thumb towards the screen. And you'll see that your fingers are curling clockwise around your thumb. So the magnetic field is going clockwise. So at point P, if you're looking at the current 1, at point P, if you just make that circle bigger, make a big circle around I1 here, with the fingers curling clockwise, that tells you that at point P, you're going down. So that is how you find a field due to each wire. So B1 would be going down. Do the same thing for I3. Draw a big circle around that third wire. I can't fit the whole circle, but just pretend you can see the whole circle. Your fingers are curling clockwise. So at point P, which is at the bottom of the circle, your fingers are going to the right, to the left. And then for current 2, we can go ahead and do that one as well. Just draw a big circle around the wire and curl clockwise. So you can see that at point P, which way we're going down and to the left here, we're going at a diagonal. So that is the best way to find the direction of each field. The reason that we care about the direction is because it tells us that to find the magnitude of the net field, we can't just add these numbers because they're going in different directions. So we have to use vector addition since magnetic field is a vector. B3 is all in the negative x direction if we define a coordinate system, x and y. B1 is all in the negative y direction, and B2 has an angle. The angle here is 45 degrees. right? Because we're tangent to that circle. And so you should be able to see that that's 45 degrees here for B2. So we have an x component and a y component for B2. If we draw it to the side where we have more room here, we're going to have B2x pointing to the left and B2y pointing down, since B2 is going to the left and downward, with our angle 45 degrees here. So to find a net field, we can think of it as separating the components, x and y. We can have B1x, B2x, B3x, B1y, B2y, and B3y. And then just fill out our chart for the x and y components. Then add up those components separately. Use the Pythagorean theorem to find a magnitude. So B1x is 0, since it's going straight down. B1y will be negative 4 times 10 to the negative 5 Teslas. B2x, the x component uses cosine and it's negative, so negative 3 times 10 to the negative 5 cosine of 45. B2y is also negative and uses sine, which when you have 45 degrees, it doesn't matter if it's sine or cosine. But just to be consistent, we are opposite the angle that uses sine. And then looking at B3, which only has an x component, negative, since it's going to the left, negative 4 times 10 to the negative 5, does not have a y component, so that's equal to 0. So then what we do to find the x component of the net field, we add up all of these components. To find a y component of the net field, we add up all of the y components. And when we add these, we will get negative 6 times 10 to the negative 5 Teslas in each case. So now to find the magnitude of the magnetic field, now that we have the components, we could draw the components if we wanted to. Bx is to the left, by is going down. So the magnitude uses the Pythagorean theorem to find B, that net field. So the magnitude of B is the square root of bx squared plus by squared. And that's going to give us 8 times 10 to the negative 5 Teslas. If we needed to find the direction of the field, we could just use the inverse tan to find it, but we weren't asked that, so we can just stop right here. Just another example of finding the magnetic field. When you have more than one wire, you have to pay attention to the direction.